So weak acids are all of the acids that are not those 6 strong acids. So there's a lot more weak acids than strong acids. Weak acids do form ions, but they only ionize a little bit. So if we look at something like HF, which is a weak acid, when we put this into water, it ionizes a little bit. In this example, we've got 1 fluoride ion and 1 hydronium ion being formed. But most of it stays as intact molecules. That's what weak acids do. They are weak electrolytes, and that means that they conduct electricity, but they do so very poorly. And so if you use that light conductivity tester, you'll see that the light is weak because it's a weak conductor. When we write the equations for these, where we're putting hydrofluoric acid into water, we use a double-headed arrow because this very definitely is an equilibrium. The equilibrium actually lies far to the left. It's mostly HF molecules and only a few of the fluoride ions. So here's an example, some pictures. There's the pure water again. Electricity will not flow through the pure water, and so the light bulb doesn't light up. If we add HF, a weak acid, same amount as the HCl strong acid, we get a weak glow in the light bulb. I'd love to be able to show you this in real life, but the conductivity detector I have is broken. So we're going to watch a YouTube video. This guy's a little bit dorky, but aren't we all?
The term electrolyte is a term used when talking about solutions with water as the solvent. We'll demonstrate the property of being an electrolyte with an electrical conductivity tester like this. Pure water does not conduct electricity. I will put the electrodes of the apparatus into the beaker of water. There's no light coming from the light bulb. If I dissolve the material in this water and the light lights very brightly, the dissolved material is called a strong electrolyte. As an example, here's a small amount of table salt. I'm going to add just a little bit to the water and stir it up. As it dissolves, the ions of sodium and chlorine, which are charged particles, go into the water, which will now allow the solution to conduct electricity. So the ionic substance, table salt or sodium chloride, is a strong electrolyte. The term non-electrolyte refers to a substance which dissolves in water but does not allow electrical conductivity. Here is some sugar, which I will dissolve in the water. As the sugar dissolves, the light does not light up. So sugar is a non-electrolyte.
Doesn't form any ions.
Some acids and bases are also strong electrolytes. Here's an example of some hydrochloric acid. Only a little bit in the water, and about 10 drops. Will allow the light to light up very brightly. So the acid is also a strong electrolyte, therefore it's called a strong acid. Acetic acid, on the other hand, dissolves but allows very little electricity to go through the water. See how the light bulb gives off much less light with a lot more acid. Thus we call acetic acid a weak electrolyte, and it is a weak acid.
Any questions? So, weak and strong in reference. Yeah, fine. Weak and strong in reference to acids doesn't have anything to do with how dangerous they are. it has to do with how much they ionize. Oh, this stupid computer. Okay. So there are lots of weak acids. You may have heard of carboxylic acids. Those are weak acids that are naturally occurring. Things like acetic acid, malic acid, citric acid. Those are all carboxylic acids. Of the weak acids listed here, hydrofluoric, acetic, formic, that's the acid that is in red ants, and when they bite, it stings very badly. Sulfurous acid, that's similar to sulfuric acid, but it has one less oxygen. Sulfuric is strong, sulfurous is weak. Carbonic acid, phosphoric acid, those are some common weak acids. There are many, many more. Sulfurous and carbonic acid are both diprotic. When we look at their formula, they start with H2. It means they have two hydrogens that can be released as ions. But they only release them a little bit, and phosphoric acid is triprotic. So if we look at these illustrations of some acids, we should be able to tell by looking at these pictures, are these strong or weak acids? So let's look at this first one. Here we have hydronium ions and iodide ions. And this would be from hydroiodic acid. Is this a strong or a weak acid? It's a strong acid. We don't see any hydrogen iodide molecules. So that one's strong. Bad S. How about this one? Here we have nitrate ions and hydronium ions. That's also strong. This must be nitric acid, and nitric acid is one of the 6 strong acids. And then over in this beaker we have CHO2 minus ions, and we have hydronium ions, and we also have formic acid molecules. Strong or weak? Weak. Any questions? Okay, so in this skill builder, they're asking us to determine the concentration of hydronium ions in each of these solutions. And this is really less of a quantitative exercise and really more of a qualitative exercise. There's not really any calculations we have to do. The trick to answering this question is to recognize, is it a strong acid or a weak acid? If it's a strong acid, the hydronium ion concentration will be the same as the concentration of acid because all of it ionizes. If it's a weak acid, it will be less. Without knowing what the equilibrium constant is, we can't tell how much less, and the question isn't asking us to tell. So when we look at A, 0.5 molar HCHO2, that's formic acid, is that a strong or a weak acid? It's a weak acid. Now, how would you know that? Well, you go back here and you look here in this table, it says formic acid. On an exam, you would know because I would give you these, and that one is not listed here. Anything that's not listed in the 6 strong acids is a weak acid. So the first one's a weak acid. So what can we know about the concentration of hydronium ions? It's going to be less than 0.5. So we would say the concentration of the hydronium ions is just less than 0.50 molar. You could calculate it using an equilibrium constant, but we don't need to, so we're not going to. What about this one, 1.25 molar HI? That's a strong acid. So that means that there are 1.25 moles of HI per liter of solution. They all ionize, right? Ionizes completely. So this goes completely to hydrogen ions plus iodide ions. There's none of this left. And all of these hydrogen ions are going to ride piggyback on a water molecule, so they're all going to really be hydronium ions. So the concentration of hydronium ions is equal to the concentration of the acid. So it equals 1.25. at about 0.75 molar HF. Strong or weak acid? It's a weak acid. So then what do we know about the hydronium ion concentration? It's less than 0.75. Any questions? Strong bases. Strong bases are ones that completely dissociate in solution. The strong bases are all going to be ionic compounds. Even if they're only slightly soluble, all of the parts that dissolve dissociate completely. So all ionic bases are strong bases. And they're going to be the hydroxides, lithium hydroxide, sodium hydroxide, etc. Now, some of these, like the group 2A metal hydroxides, have 2 hydroxide ions for every metal ion. So those are equivalent to the diprotic acids. We don't really have a name for them, but these bases that contain 2 hydroxide ions, when they dissociate, they do so in one step, unlike the acids, which do it in 2 steps. So strontium hydroxide will release 2 moles of hydroxide ion for every mole of this that's dissolved. Here's our illustration. Sodium hydroxide is a strong base. You put it in water, it completely separates. It dissociates into the individual ions. There are no intact formula units floating around. They all ionize. Weak bases are similar to weak acids. They produce ions, they produce hydroxide ions in solution, but only a little bit, okay? I always wonder what's going through the head of these engineers. You know, some of them just toot very politely, and some of them just really go to town. I don't know, maybe he's just like got indigestion or something. He's taking it out on the rest of us. I like the Amtrak ones. They sound so sophisticated and polite, though. Toot, toot, right? And it's the freight trains that are so much louder. They're tired. Yeah. Oh, I'm tired, too. Okay, weak bases. As bad as the squirrels. Most of the common weak bases produce hydroxide ions not by dissociating and releasing hydroxide ions, but actually by accepting a proton from a water molecule. So they're acting as Bronsted-Lowry bases, not as Arrhenius bases. So here, B meaning weak base, just any weak base, reacting with water to form BH plus and hydroxide. So remember, the base is like the babysitter for that hydrogen ion. This is acting as the acid, donating the hydrogen ion to the base. So now here's the base with the hydrogen ion, and what's left of the water after it donates a hydrogen ion is the hydroxide ion. And that's how a base, a weak base, forms hydroxide ions. So the most common weak base is ammonia. It's really the only one we're going to deal with much. NH3 reacts with water to form ammonium ion and hydroxide ion. And these are weak bases, so they do have the double-headed arrows because this is definitely an equilibrium. So here's ammonia being put into solution. It does act as a base and accepts a hydrogen ion, forming a hydroxide ion from the water, but we also have a lot of intact molecules present, and that's what distinguishes it as a weak base. There's lots of weak bases. Most of them are organic amines, which you may or may not have heard of. These guys, pyridine, methylamine, ethylamine. We're not going to do anything with those. You do need to know about ammonia. Bicarbonate ion is also a weak base. You might recognize bicarbonate ion as the ion produced after carbonic acid acts as an acid. And so this is really the conjugate base of carbonic acid. it can accept a hydrogen ion from the water, and then we get back the original acid. So carbonic acid. Bicarbonate ion, sodium bicarbonate, is a very useful thing to have around in the lab because it can neutralize bases and acids. And so that's pretty useful. So we can do a similar thing with looking at hydroxide ion concentrations in solutions of bases. So again, we need to ask ourselves, is it a weak base or a strong base? So this first one, barium hydroxide, is that a weak base or a strong base? It's a strong base. Anything that's an ionic hydroxide, barium hydroxide, sodium hydroxide, anything metal ion with hydroxide is a strong base. Well, now we need to be a little bit careful. When this dissociates, we're going to get one barium ion and how many hydroxide ions? 2. So for every one of these, we get 2 hydroxides. So then in this solution that is 0.055 molar barium hydroxide, what's the hydroxide ion concentration? It's twice, right? And you could do this as a mole-mole stoichiometry problem. Here we know the concentration of barium hydroxide. Let's just start this over here. 0.00, too many zeros. Moles per liter barium hydroxide. And then we want to know the concentration of hydroxide ions. So we look at the ratio from this equation. We get 2 hydroxide ions for each of these, 2 to 1. So that gives us what, 0.110 molar? So the hydroxide ion concentration is twice as much as the base because this base contains 2 hydroxides. Does that make sense? How about this one? C5H5N. Does that look like a strong base? It probably doesn't look like a base at all to you, right? This is related to ammonia. You see this N in here. This is a weak base. So just like with the strong acids, there's 6 of them and then everything else is weak. For this class, metal hydroxides are strong bases. Everything else is a weak base. So if this is a weak base, what does that tell us about the hydroxide ion concentration? It's less than the 1.05. How about sodium hydroxide? Strong or weak base? Strong base. How many hydroxides are there in one unit? 1. So that tells me that the hydroxide ion concentration is going to be the same as the concentration of the base. Because each one of these separates and forms one hydroxide ion. Any questions?